President of the Statistical Society of Australia for the South Australia branch. On behalf of the society, I want to acknowledge that we are meeting on the traditional country of the Ghana people of the Adelaide Plains and pay respect to elders past, present, and emerging. So thanks for joining me today, either in person or online. Before we start with our presentation, I just would like to extend my usual invitation to get in touch with me or other members of the council if you would like to present at one of our monthly events, because we're always looking for presenters and we welcome a wide range of topics. I'm already pointing at someone here, and techniques. And likewise, I'm happy to assist you if you have any ideas around organizing or delivering a workshop. Also, a reminder to have a look at the Statistical Society website, especially in the Career Center, if you're interested in the, changing your career or seeing what's out there. That's where the current position are advertised. So today our presenter is joining us online. And so I sort of would like to invite people to leave their cameras on so that Adrian doesn't feel like he's talking to an empty room. I'd like to then introduce today's presenter, Professor Adrian Barnett. Professor Barnett graduated from the University College of London in statistics in 1994. And then after that worked for SmithKline Beecham at the Medical Research Council as a statistician before coming to Australia to do a PhD. He then completed his PhD in mathematics in 2002, and his main interest is how to increase the value of health and medical research. I think we got it on a topic that is very important to Professor Barnett, which is the cases of bad statistics in medical research. Annie, sorry, could you help me with this? Just can see that short. So.
I can't see it. Wait.
Oh. Okay. So with that introduction done, Adrian, if you want to take the stage.
Thank you, Barbara. Hopefully you can see my slides.
Yes, we can.
Yep. Great. Yeah, and interesting to mention my first job there with the drug company, SmithKline Beecham. I might come back to that later on because I think it's actually very influential for the way things have turned out for me. And so here's a little cartoon by David Parkins. I've got another one of his cartoons later on. This cartoon appeared in Nature, and it's kind of funny, just highlighting the ways that researchers who might be very good in other areas and very clever in other areas sometimes do get caught out by numbers. So that's going to be at the heart of this talk. And I live and work on the lands of the Turrbal and Yagara people, and I acknowledge that QT stands on a place that was always been a place of teaching and research, and I pay my respects to their elders past, present and emerging, and acknowledge that the lands were never ceded. Okay, I want to start with this paper published pretty soon after the pandemic really got going in the Lancet. And it was a prediction model, which I'll come to prediction models again later. It was a prediction model of mortality in hospital. And then when you read the methods, you see that there were 813 people hospitalized, 613, 75% were excluded because they were either still hospitalized or not confirmed as infected. So the first thing to say about that is terrible reporting. They should have said what percent were excluded because they were still hospitalized and what percent were excluded because they were not infected, because they are two completely different reasons for excluding people. The next thing is to lose 75% of your sample in that way, that can be potentially very biased. And if a decent percentage of that were excluded because they were still hospitalized, then the biases in a survival model could be huge. If these people who are still hospitalized were obviously still alive. So if you're trying to do a model of mortality where you exclude people who are still alive, that can be really horribly biased in the way of a sign bias, that you get not even, an inaccurate estimate of the true effect. You get the effect in the wrong direction. So I was pretty flabbergasted that this was published in one of our premier medical journals, The Lancet. But then, The Lancet didn't do too well in the pandemic because they also had the Surgisphere scandal, which is worth reading up on as well. And there are two implications, I think, to take from this. There's probably more, but anyway, two that I focus on, is that bad research is not restricted to low impact journals. This is one of the highest ranked journals. I'll come on to the ranking in a minute. And this is just, this is the sort of thing I would fail an undergrad student for. Doing a survival model and excluding people still alive is really, really shocking from a statistician's point of view about how biased that is. So for that to get in one of the best medical journals was really quite a shock. And people said to me, I've commented on this on Twitter, and people have said, oh, well, there wasn't any time. They had to publish straight away. Well, two things with that. Number one, why did scientists think that it was a good idea to lower standards during the pandemic when the world was looking to science to help with the pandemic? Why on earth would we rush stuff and publish hastily done research? That was a really silly thing to do. And I think we're lucky that things like the recovery trial, which was an excellently executed trial and had a lot of pre-planning that was sort of ready to go even before the pandemic started. We were lucky that did so well. And obviously the fantastic work done on the vaccines as well. But people like this, I think, really let the side down. The other thing is you don't have to wait until everybody's died or discharged. You can do a survival model and you can censor people, but they seemed unaware of that method. They used logistic regression. The other implication is this paper has been cited an incredible 25,000 times. So that says to me that a lot of people don't recognize or just skip over that sentence or do not understand the major statistical flaw that this paper has. And I don't think the Lancet do either. So I wrote to the Lancet as soon as I read this paper, so a day or two after it was published, because some colleagues wanted to know if they should do the same thing here or get ready to do the same thing here in Australia. And they told me they didn't have room to publish my letter expressing these concerns. And of course, I mean that the authors could have easily reanalyzed the data and provided a little update that would have given much better evidence right there and then. Anyway, all the Lancet do is brag about how good their impact factor is. So you can see this tweet here, while impact factor is a partial measure of our reputation, yeah. But anyway, we're number one, and we've got an impact factor of 202.731. Well done, us. Well, if you take off those 25,000 citations to that paper that I believe is fatally flawed, they're not number one anymore. So this, this getting to the top of the pile is done on the back of at least one shoddy paper. And I mean, I haven't looked at some of their other papers. And what this reminds me of, I don't know if anybody saw this, but the most recent winner of the French Scrabble title does not speak French, which is kind of a funny thing. This guy just learned all the words and, obviously has some sort of photographic memory and was able to get it all down and beat all the natural French speakers. This is, for me, is an analogy to the Lancet. And so not just the Lancet, some of these other big journals, they've totally lost the point. They're focusing on these silly games, these silly sideshows. Like impact factor is a really flawed measure. And there are known ways that journals can increase their impact factor. They can be gamed. And they are gamed. As soon as, this is Goodhart's law, as soon as a measure, as soon as something becomes a target, it ceases to become a good measure. And that has happened with the impact factor. And I think it's worrying because, again, at this time in our life, science is massively important. We have the climate crisis. We've just come out of a pandemic. We've got other antibiotic resistance. We've got an aging population. We've got, huge problems with things like suicide that are not going away. We really need science to be fully functioning, and we really need our top journals to be focusing on what really is quality. So I find it utterly depressing that they're engaged in these sideshows. And I really hope, I think preprints have been an amazing innovation, and I really hope that preprints undermine these guys and their business model. Not to mention, I am going to mention the massive profits that these journals make as well, all out of our hard work. And then this is a nice quote from Gauss. Lack of mathematical education does not become more evident than by excessive precision in numerical calculations. So Gauss of the Gaussian distribution, even back then, people were using too many numbers. And here's my little joke. Here's Gauss's birthday from 1777.241 to 1855.145. Of course, that's not how any of us would present his birthday, but of course the Lancet would, because they quote impact factors to 3 decimal places, because of course that 3rd decimal place is really important. Actually, that 3rd decimal place is probably a pretty good proxy for a random number generator, but anyway. Okay, another little bugbear, and I should say this talk is more designed aimed at clinical colleagues, and I appreciate there's a lot of statisticians here today, but let's talk about this stuff anyway, because it's kind of interesting. Another bugbear I see people in medical research, the same mistake I see them make over and over again, because it has become absolute dogma, is that they will get their data, and here I've done, this is data I just made up, data on blood pressure. And if they're smart enough, they will draw a histogram or a box plot, and they will look at this, and their immediate reaction will be, oh no, the data is not normally distributed, therefore I have to use non-parametric tests. And you will see in papers where people will say that they've tested every single variable using the Kolmogorov-Smirnov test or whatever, and then rejected if it wasn't normal. If you want normal data, if you want perfectly normally distributed data, one of the best ways to get that is just purely by measurement error. Measurement error will often be beautifully normally distributed. If you're not in the business of measuring measurement error, if you actually want to measure something exciting, then you really should be celebrating lumpiness in your data, because lumpiness in your data is a sign that something is actually going on. So for example, I mean, this is a very contrived example, but maybe when we plot this histogram with 2 groups, we see one group with all lower blood pressure and one group with all higher blood pressure. This is an amazing result. This is a once in a career result, something to be celebrated. There is variance in your data that is explainable by some group. That is amazing. But it's incredible how few people realize this, and how many people shy away from lumpiness in their data, and outliers too. The number of times I see people exclude an outlier just because it doesn't fit. And actually that outlier can be the most interesting observation in your data. What the hell happened with that outlier? Maybe there's something really interesting that happened there that tells us a lot about the data generating process. But no, people or researchers have been trained somehow to sort of smooth these things out. All right, on to p-values. And I'm sure you've all seen this cartoon from XKCD. You see this, and I've heard this. I once had somebody, I made the mistake of doing a stats consultancy in front of somebody, and yeah, they ran out of my room crying when the p-value was above 0.05. So again, this is something that researchers have been trained to look at, to the detriment of, or to the expense of, everything else about their experiment. You just look at the p-value, and the p-value tells you everything you need to know. And then very smart people do this. It would be amazing if anybody could invent a statistic that would do that. Imagine if there was a statistic that could tell you, that could pick apart successes from failures, that could pick apart signal from noise, you know, in any circumstance. That just does not exist. The p-value was never designed to do that. But unfortunately, it's become this kind of gate that studies get published on and studies don't get published on, and entire careers can be made on a p-value. And I often think the one thing, if you could think of one simple thing to change in health and medical research, or in what treatments we receive in hospitals, in GP clinics, if the p-value threshold was actually at 0.01, the 0.05, I can't think of a sort of more minute change that could actually drastically change research and also policy and practice. And it's bizarre that the arbitrary threshold has so much power. And it leads to hilarious, this is in a paper, it leads to hilarious graphs like this one. So these people took people aged less than 40 and aged over 40, and then they tested a difference in their age. Hey, presto, we've got a small p-value, we can publish. I mean, this is just shows the mania around p-value, that it can lead people to do things like this that are just so daft. All right. Now, I know the statisticians, but let's have a go. One way I like to undermine p-values with medical people who tell me how important they are. And this is a fun thing to do. Next time a clinician asks you for a p-value and you say, no, I don't think we need that. If they say, yes, I think we do, ask them there and then on the spot to define what a p-value is. And I swear that most of them will get it wrong. So you can either you can do this on your phone, or you can do this on a computer, obviously. So there's two ways you can do it. You can either put in that whole HTML at the top there with the code, or you can just go to menti.com and use the code 32057080. And let's see how many people get this right. I hope you beat the clinical audience I did the other day. Although they got the modal answer was right, but still more than half the people got it wrong. I'll just have a little bit of silence. Now, hopefully you should, if you go to the voting screen, you should see something like that. And then, let's have a look, see if people are getting results. Oh, we've only had 2 votes. Maybe people are so disgusted with having to do this. Okay, well, all 2 of those are right. I will skip over this. But look, it is amazing the number of clinicians that you meet that think one of the most common wrong answers is that first one, that it is the probability that the null hypothesis is true, when actually, oh, the code isn't working. Sorry, that's why I only got 2 votes. Yeah, sorry, Menti does seem to change the codes every now and again. You know, a p-value assumes the p-value is conditional on the null hypothesis being true. So it doesn't tell you anything about the probability of the null hypothesis or the alternative hypothesis. You know, the correct answer is that very last, long, boring one there, the one that actually makes your brain hurt to think about it. You know, it's actually about the probability of the data, not about the probability of the hypothesis. So the point of this slide, when I show it to clinicians, or when I talk about this with clinicians, the point of this slide is to show them that they're enslaved to this p-value statistic, and they don't even know what it means. And once, when somebody, very confident person, I asked them what a p-value was in front of a bunch of other people, and they got it wrong. And I said, that's wrong. Their immediate answer was, well, that's okay, because this is the way that everybody thinks. Everybody's getting it wrong in the same way, and this is what everybody thinks it is. So then that's okay. Which is just crazy. I mean, how unscientific is that? You know, I'm not using the right definition, but because everybody I know is not using the right definition, then somehow, I don't know, the statistics and the mathematics will actually change to suit your definition. You know, that's just simply not the way that these equations work. They were probably just trying to save some face. And I do feel like a mean statistician sometimes when I pull people up especially when they're not on their own and they're in front of other people. But basically, I'm just sick and tired of p-values and how slavishly they're used. And then, I mean, this is another reason why I get so annoyed with p-values. So this is some work that we did. We automatically extracted ratio confidence intervals from Medline papers between 1976 and 2019. And then it was actually Eric Van Sweat. We shared our data, and Eric Van Sweat came up with this plot, which was much better than the plots I did to try and highlight the problem. So what you can see here is, so these are all the Z values extracted from the confidence intervals. And the key thing is here, it sort of looks like a normal distribution that's just been caved in. We've got this massive hole of non-significant studies, and I think you can see, just either side of this significant line, on the negative side and on the, positive result and a negative result, both either statistically significant positive effect or negative effect. You see this huge sudden spike in significant values, or in values, and so that dotted line, anything in the darker red will be a p-value below 0.05. So this is a serious problem. There is, and I have called this research misconduct, and I've been pulled up a bit on Twitter about this recently, saying maybe that's a bit of an overstatement, but I think this shows that our evidence base is horribly biased. People are either reanalyzing their data until they get into one of these tails, or they're collecting more data until they get into one of these tails, or they're switching their outcome, oh, we're going to look at blood pressure, but now cholesterol is significant, so let's just present that instead. Or they're just simply not publishing these negative studies, which for me is also research misconduct, because somebody's giving you the time and the money to do that. And if you don't publish it, you need to publish negative studies. And there have been numerous cases where there's been direct harm from negative studies not published. Even if there's no actual harm to patients, somebody else might just end up repeating your study and then wasting their time and money too. The Lancet's impact factor will go down if we publish negative studies. Yeah, look, I think journals journals are definitely to blame for this. I think they're definitely part of the problem, and peer reviewers, and there's some really neat randomized trials as well where they varied the p-value and showed very, very big differences in acceptance rates depending on the p-value, even for an identical study. But I think us as researchers have a lot to bear for this too. We're the ones feeding this beast. We're the ones who are suppressing negative results for the sake of our career. And I just don't think, well, I know that isn't right, and it's depressing. And I worry about the state of our evidence and what policy decisions are being made on something that's clearly horribly biased. And we shouldn't just think this is overseas. So, the NHMRC did a survey of people and of Australian researchers. In the past 3 years, how often have you not attempted to publish a valid negative or neutral study? 25%. So you can see straight away there, that's partly explaining that huge gap we have in negative studies. Selected the statistical method that provided the desired result, 8%, but that increases to 30% if you ask them, have you seen other people doing that approach? So, we're less likely to admit it in ourselves, but we certainly see it elsewhere. So, this is clearly going on in Australia. This seems to be going on everywhere. It is an incentive that is horribly baked into our system. And I think we really need to get away from using p-values and move towards confidence intervals. Of course, confidence intervals have the same problem. That graph was drawn on confidence intervals. But so I've actually had a self-imposed ban on p-values in any papers, and I've gone for about 18 months now. And the one thing I'd say is, when talking to clinical colleagues, is I have a much more nuanced conversation now about the odds ratio or the mean difference or whatever it is we're looking at. Have a much more interesting conversation about, well, is that a big difference? Is that going to make a difference to people's lives? Rather than just before them just scanning, looking at the p-value and going, oh no, or oh yes. you know, which is not a useful conversation to have after all that time and effort on the research. Another way I talk to colleagues about abandoning statistical significance, this is the most complex slide, but anyway, I'll go through it in detail. So first of all, I'm going to imagine I've got a real effect. When I have a real effect, I'm going to be able to find it 60% of the time, and I'm not going to find it 40% of the time. So, you know, I'm assuming a statistical power of 60%. So my experimental setup is pretty good. More often than not, it will find a true effect. Now, like my p-value, I'm going to imagine I don't have an effect. And 5% of the time, so I'm going to use the magic 0.05 threshold, I actually do find a result. I believe there is a difference between groups when there's not. So I'm going to make a mistake 5% of the time, but I'm pretty good. You know, 95% of the time, when there is no effect, I correctly mark that as a true null. So this doesn't seem like a bad world to be working in. However, we have to think of the baseline probability now. I'm going to imagine I do 200 experiments during my career, and I'm going to say in 20 of those experiments, there's a real effect. And again, this got a bit of attention on Twitter, people saying that's horribly pessimistic. And how can you think that scientists are that dumb that they only pick a real effect 1 in 10 times? Well, what I would say to that is the success rates for animal studies are something like 1 in 1,000 hit rate from an animal study to a therapy that makes it to humans. So there are a lot of null effects in animal studies. If you go to phase 3 randomized trials, it gets much closer to 50-50. But even at the stage we've got to a phase 3 randomized trial that has a lot of work gone into it, we're still only 50-50. So for me, a real effect of 10% feels about right. Now I'm plucking that. Yes, I am plucking this number out of the air, but a lot of stuff just doesn't work because of complex chemistry, biology, social behavior. You know, the world is a complicated place, and also a lot of the easy stuff has been done, and there are these very nice meta studies showing that effect sizes have been declining over time. So real effects are getting smaller because we're looking at more marginal gains in health. Anyway, if you don't believe my 20%, you can do this little exercise for yourself and change all these numbers. So 20 real effects, I find 12 of them and I miss 8 of them. So not doing too bad. But the majority of experiments go down the no effect route, in which case of these 180 experiments, in 9 cases with my p-value threshold of 0.05, I falsely claim that there's something going on. And 171 times, so most of the time I do get that decision right. I do find that there's no effect. So now my actual false positive probability, because I don't know which one of these boxes I'm in, you know, it doesn't, I'm not told if it's a real effect or not. We're just trying to estimate if it's a real effect or not. My false positive probability is actually the probability of the number being in this box divided by the total of being in either box. So it's 9 divided by 9 by 12, which is 43%. So the false positive probability is not 5%. In this scenario that I've done up, it's 43% and possibly higher depending on how you change these assumptions. But the point is that a lot of people think, again, magically, that a p-value is sort of independent of the context or any prior probability at all. And it's not. In the long run, even if you find a p-value of 0.05 in this kind of world, which I think we're in, you're actually probably wrong almost half the time. So I think people really need to bear that in mind and maybe be more stringent with their p-values. So here's a nice quote from Yates and Healy in 1964. Significance tests are popular with non-statisticians who like to feel certainty when no certainty exists. I think that, you know, that was a very wise comment for back then, because as I've alluded to earlier, you know, these p-values are taken as this sort of written in stone measure of certainty, when in actual fact they're not. They still can be a useful statistic, but people don't seem to understand a lot of the problems that they have. Also, this is more work by Eric van Zwet, very nice, Zwet, sorry, not Zwet, Eric van Zwet from Holland. He looked at papers published on the Cochrane database and had a look at the actual power from 20,000 randomized trials. So, these are randomized trials that we think are the gold standard and are normally done to a higher standard, or we hope. Well, the median power in all those 20,000 trials is just 13%. So in that diagram earlier, I presumed it's 40% power. So actually with 13% power, that false probability for the p-value would actually be a lot higher. So in one way, I'm being very generous. And again, I think this, this underpoweredness is again a sort of possibly something that's driving this is this rush to get studies out. No, we can't wait and recruit more people. We have to get this paper out. I need this paper for my fellowship, for my promotion. Let's just publish it now. This rushing to get out trials that are underpowered and too small. And then this is some really nice work that people have done on registered reports. So if you don't know what a registered report is, this is sort of the way science should be done, is what I like to call it. So in a registered report, you write up your methods, exactly what you're going to do, like sort of like a protocol, really. That gets sent to the journal. The journal then decides if it's going to accept or reject your paper based on your methods and commits to publishing the results as long as you followed the experiment, as long as you didn't go off piste and do some other crazy experiment. And you can see, let's have a look at what happens here. In registered reports of these three different types, the percent of null findings was 60%, 70%, 60%. So again, earlier, when I was looking at 90% effects being real, this backs up, or at least I know it's not up by 80%. Did I do 80%? 1 in 10 I did. No, I was a bit more pessimistic compared to this. But still, this is quite a high failure rate when people commit to following through what they're actually going to do. And then have a look at this over here. In the traditional literature, the percent of null findings is around 10%, which is just unbelievable. Again, going back to that Z value curve, that's that center of the curve, that missing chunk of null findings is just not there. Because people are either just not publishing in the traditional literature or are reanalyzing their data until this null finding goes away. So this graph for me is really striking and clearly shows a massive difference between high quality evidence that's much more likely to get at the truth compared with our current scenario, where I'm really worried that a lot of papers that are published are not an accurate picture of what the data are actually showing. Okay, I want to talk about prediction models, because this is something we come up with over and over again with clinicians. And I've always liked this slide for type 1 error, you're pregnant, type 2 error, you're not pregnant. So I'm not sure why. I'm with Nicole White. We're going to be hopefully doing some work on this. But I do find it really interesting working with clinicians, how keen they are to get a prediction model. They really love the idea. And with the big data and more data, a lot of them seem to think that, well, you just get lots of data and throw data at the problem, and a prediction model will work, and we have these statistical algorithms that can make it work. I've only met a few who really do understand that for some stuff it's just never, ever going to be predictable. And in some areas, there is inherent stochasticity in people, and especially like elderly people who come to hospital with all this past history have these really complicated interactions that can cascade in the hospital. And when I see prediction models in areas like that that have an accuracy of 90% or above, I'm actually kind of suspicious, because my experience is you cannot predict things like length of stay or probability of dying in that population, because, thinking in a sort of frequentist way, you could get exactly the same data set. If you could go back in time, get exactly the same data set and run those people through that bit of their life again, you would get a different answer, because why certain stuff happens to people is massively complicated, potentially dependent on things like, did they have a good night's sleep last night? What time they took a pill, what they had for breakfast, all these weird little cascading events that can end up then putting them on this trajectory that I just don't think any amount of data is ever going to predict. And something that I found really depressing, again, this is going to the pandemic, this is work done by Laurie Weinatz and colleagues, including Gary Collins. These guys looked at prediction models developed during COVID. So there were 232 prediction models developed that they found during COVID, either to predict who was going to get COVID or not, if you got COVID, who would end up hospitalized or not. And I think the last one was if you ended up in hospital, who would die or not. Okay, so all 232 prediction models, there was only one that was a low risk of bias. There was only one that was any good. 1 out of 232. I just find that utterly depressing. But it's also utterly predictable, because I've done a lot of different studies, all sorts of different studies, probably almost, every common health and medical research study I've done, every common design I've done at least 10 or 20 times. Diagnostic and prediction models are the hardest model to run. They're the hardest study design to do. There are so many things that can go wrong. If you want to have a look at it, you look at the, the Equator guidelines that tell you all the things to mention in your study. Have a look at the Equator guidelines, the STAR-D guidelines. There are so many different ways that bias can creep in to diagnostic and prognostic models. Yet a lot of these things are ignored. And that's why, you can see in this graph, people doing so badly on a lot of these things. And a lot of the time you can see it's just unclear, the yellow bar there, because researchers are just not mentioning what they do. So I do find it bizarre that clinicians seem to think they can do these models themselves. They just grab some data, run it through some algorithm, often horrifyingly things like, stepwise selection and things like that, and think they can get an accurate prediction model with very small sample sizes, with no idea of internal or external validation. And then this is a nice, it was Martin van Smeeden, I think, who did this little flow chart. Are you thinking of developing a prediction model? Is it needed? Well, I'm not sure. Stop. Who's it going to be for? Well, I don't know. Stop. Do you have patients with these characteristics? Well, sort of. Stop. Is there an existing prediction model? No. Check again. Oh, there is. Stop. So there are just so many of these hurdles. Oh, there's a second bit to the graph. Have you got a large data set? And large, really, there's rules of thumb around, but large for a prediction model, and I know this is rule of thumb, and I could be pounced on for this, but I'm really looking for data sets that are around 1,000. And it's so rare that you see that. Or on the other hand, you do get these massive data dumps from the hospital that can be like 100,000. But they then tend to have some very serious biases in their data generation process, and there's a whole load of people that you're missing. So really the only way, and then in this last box here, here are all the things you need to do. So I've become so upset with this issue that I'm actually making a recommendation that medical research funders should no longer fund projects that plan to develop a prediction model unless a qualified statistician is a principal investigator. Now, obviously, I'm a statistician, and there's an economic term called rent seeking, which is just a sort of way of, businesses trying to monopolize markets and trying to get all the business that they can. So you could accuse me of saying, well, Adrian, you're just trying to muscle in here and make sure that you and your statistician buddies get all this work. That's not why at all. I am seriously concerned, and we all should be seriously concerned, that out of 232 prediction models for COVID, only one was of any value. And it's not just COVID. Lots of these other prediction models are really low quality, yet they continue to be published. So this may be harsh, but I really think we need to stop, and people need to be much better trained in this area. Or they need to start working with statisticians, because we're producing a whole load of stuff that at best is just wasting people's time and getting published and ignored. At worst, you know, I shudder to think if any of these rubbish models actually get used in practice. All right, some other work I've done. This is just a bit of a what we were looking at statistical method section in clin trials. Actually trying to see, you know, what do people write in their stats method sections? And I'll just run through. I kind of came up with this Olympics for the worst ever stats method section. So in the bronze medal position was t-test. That was it. That was the entire statistical method section, just the word t-test. That's it. A t-test will solve everything. And a t-test, you know, is actually a remarkably good statistic and can actually solve a hell of a lot of simple problems. I'm a big fan of the t-test, but for that to be your whole section was pretty shocking. All right, in the silver medal position, we have SPSS. That was it. That was it. That was the entire stats method section. So, you know, this idea that you'll just get the data, point a computer at it, and it will give you the answer. But there was a worse one than that, would you believe? The gold medal winner goes to the person who wrote SSPS. So they couldn't even correctly spell SPSS. And I would say this is a great reason for learning R, one of the great reasons for learning R, because it's really hard to make a spelling mistake when you write R. So, of course, I'm going to quote Doug Altman a lot today, and I quote Doug Altman a lot anyways, but I really like this quote. Many people think that all you need to do statistics is a computer and appropriate software. And I do see that attitude a lot, and especially around, you know, some of these fancy algorithms. And I'm not against all the fancy algorithms, but no algorithm works without brains. We still need clever clinicians. We still need clever statisticians to work together to work out what data should go in, what the answers mean. But I think too often people just think that they can just chuck all their data into some fancy new algorithm that they've heard of, and it will give them the answer. And of course, it will give them a answer, because the algorithm's not clever enough to say, you've asked a stupid question. The algorithm will always find, you know, the most efficient answer, but that can often be complete nonsense. All right, little sideshow on figures. And again, another cartoon from XKCD with the quality of graphs. It was getting better until PowerPoint came along and Excel. Let's have a look at some. Look at this one. This is just a complete waste of space. I've no idea why this was needed, why it had to be 3D. These are all published. These are all published graphs, by the way, that I'm about to show you. This one's even better though. I mean, you know, it's actually sort of hard to read and really distorted the data terribly. I mean, you know, that's 25% over there. It doesn't look anywhere near like a quarter in this kind of weird tiddlywink thing that they've done. And I really don't understand what these people thought they were doing and why this couldn't be presented in a table. This one is just hilarious. It just looks like sort of pieces of fudge. Nobody can tell what number that is. You cannot reference that number, or particularly this one that's even further away from the scale. You can't tell what any of these numbers, percentages, actually are. And then they actually used a font where the word sunburn looks like sunbum, unless they actually did write sunbum. It's impossible to tell if that's an M or an RN. But this is the worst one ever. This is actually genius, how bad this is. Let me run through all the problems. So we've got 6 pie charts here. There's no labels in any of the pie charts. And all the figure legend said was something like figure 1 pie charts. There was no detail in the legend. The pie charts are different sizes. That one's smaller than that one. No explanation of that. We've got moire patterns here where it's very, very hard to read the numbers. I think it's this one and another one. The numbers don't add up to 100% with no explanation of that. We've got varying decimal places. We've also got too many decimal places. Gauss would be rolling in his grave. We've got the legend here where it's very hard to tell I think the no comment is the stripy pattern, and I think the disagree is the sort of more hatch pattern. But it's not easy. I mean, they've made their legends quite small here. And then the last one is just to top it all off, there's a spelling mistake there as well. So this is actually genius to create a graph this bad. And of course, you should just stop using pie chart. I love this graph, this little plot. I show this to people all the time. Stop using pie charts. And I say to people, okay, tell me if the yellow in that one is second highest, third highest, and for, for each graph, tell me if yellow is first, second, third, or fourth. And you simply cannot tell. The yellow one, you can't tell. It's really hard because pie charts are a nonlinear transform of data and they do not work. As soon as you see the bar chart below, you can exactly tell the ordering and which one's top and which one's at the bottom, because bar charts just work. So people should just stop using pie charts. But again, like pie charts are everywhere. So if I see somebody with a pie chart now, there's two things you think. Either they don't know what they're doing, or they do know what they're doing and they're deliberately trying to hide something. So you may not stop using prediction models, but please stop using pie charts. Okay, so what's going on? Why is everything, why have we got to such a bad state in health and medical research? So a quote I've used over and over again is, this is everybody's problem and nobody's problem. And there's a nice, well, an unhappy analogy in the UK. So the UK train system used to be one company. It used to be National Rail. It was one company. They did everything: the food, the tickets, the stations, the lines, the carriages. And then thanks to Margaret Thatcher, one of the terrible things she did, the company was split up and privatized to make the maximum amount of money out of each one. And, the idea was to provide maximum services. What happened was that fixing the tracks and maintaining the tracks was the least profitable part of the company. So nobody wanted to do it. And of course, what happened was we had multiple train derailments in which some people were killed, simply because it was not a profitable part of the business, because track maintenance has to be propped up by the other parts. And once you split it into multiple parts, it just doesn't get done. So my analogy is statistics is the same for that. Lots of people want to just get on the train and do their analysis or do the exciting stuff. Nobody wants to spend any money on statistics. Nobody wants to spend money on this stuff. And I've even seen, there was an institution I was involved in where they had a serious problem where PhDs were getting failed because their stats were so bad. There was a big investigation. We all agreed we need to employ more statisticians, but then nobody wanted to pay for it, as if they would magically come out of nowhere. So for some reason, we are just not valued in the system, even though we're having the equivalent to trail derailments in statistics. We're having the equivalent to these papers that are just absolute statistical nonsense. So the warning signs are there. And this is a nice cartoon, again, from Nature. So at least Nature is trying to take this issue seriously. Here are all the groups trying to hold up science: the funders, the journals, the researchers, the institutions. None of them are spending any money on quality control. None of them. The funders don't have a budget for that. The journals, well, they probably say that peer review is doing the quality control. It's simply not. It's been shown over and over again that it doesn't work. It certainly helps, and I'm not suggesting we get rid of peer review, but it is not doing proper quality control. Researchers, we're just too busy. The institutions are certainly more than asleep. I think when there are these scandals, when things go wrong, the institutions actually sort of close ranks and try and hide these things because they're simply thinking about their reputation. So what can we do about quality control? Well, my pitch is that we use a system that's well used in agriculture and industry, where we randomly audit. So we would randomly audit 100 papers per year from each university and research institute. Statisticians would then check those papers, check how well written up they were, check if they used the right analysis, and then see if we can actually get the data from these people and reproduce their results. That would massively shift the goalposts. That would massively send a very strong incentive to all these places that you really need to worry about the research quality in everything you do. Because a lot of research institutes and funders do this as well, and I can kind of understand. We'll just focus on those things that work well. And I'm glad, I'm very glad that there are those things in science that work really well. But just focusing on the shiny ones that made it through, you know, you're ignoring all this poor quality stuff that's underneath. And if we can raise the quality of all that research, then we'll, you know, humanity will progress much faster, and we'll have much more efficient hospitals and a much longer and happier lives if we could do this. So the gains are actually massive. Of course, this would cost money, maybe depending on how many statisticians you're going to employ, but sort of, you know, ballpark 1 to 2 million per year. But I really think it's got to the stage where we need this. This needs to be an independent body, and it needs to be seen as important by these institutions. The other thing I've been working on is sort of statistical robots. So because there simply aren't enough of us to go around, we can actually use robots to, and there's a group of us doing this called the Automated Working Screening Group. So we will read your paper using a robot and we can flag certain things in there that look a bit wrong. And I'll just give one example. I'm sorry, I am coming to the end. I'm conscious I've gone a bit long, sorry, because I've been getting angry rambling going on. So here's some papers or tables from randomized trials by a now discredited researcher called Sato. One thing you can see here, so he's done these randomized trials. Straight away, you should start to see some patterns in these 4 trials. One of them here is retracted, and you can't actually read the data anymore, which is a bit of a problem for me when I'm trying to use his data as examples. You can see that in every treatment group here, there were always 15 people, same here. And in every treatment group, there were exactly 7 men and 8 women, 7 men, 8 women, 7 men, 8 women, again. In this one, 8 men, 7 women, but again, perfectly matched. And also, if you look at some of the numbers here, some of the continuous numbers, and you've got a bit of an eye for these things, you'll see that they just don't seem that variable. So this is a person who was just making up data. And they were, you know, in a randomized trial, the standard table one is, well, here's the group characteristics. And clearly randomization has worked well because, you know, they're all very similar. Well, what this person seems to have been doing was to make up data and to try and pass that test to get it through peer reviewers. They were making this data that was just, you know, too good to be true, too similar. And if you think that this only happens outside Australia, well, I'll encourage you to have a look, and I'll only refer to what's publicly available because this is about to go before the courts, I believe, so I should be careful on what I comment on. But have a read of these, you know, of what this researcher has been accused of, because it seems very similar. Okay, so we can look at a Bayesian model, and I've made a little Bayesian model, and I did 2 things to sort of look at the dispersion in those tables, because we know what the dispersion should look like if things have been properly randomized. So we can then have a look if this sort of t distribution is under dispersed, where we've got sort of all the groups are too similar, or over dispersion does happen as well when people make up data because they don't understand how to do it well. So, and then what I did with Sato's work is I looked at sort of this accumulating evidence, because I presume that the sort of probability would go low and then start higher over time. Actually, you know, the probability was at 1 from the very first trial that they published and went on. So, and then you can see the sort of precision multiplier here, which shows that that his results were clearly under dispersed, and you can see the uncertainty narrowing there with more data. So what I would say is, and you know, I've written this code, and it does, I've also made that it automatically can read a paper, find the table, extract the numbers, run a model. So if this automation would have been in place earlier, then I think we could have caught this person earlier and stopped them publishing this rubbish, or at least raise some questions with the journal. And we're trying to work with journals to get this out there, so that we can not just look at fraud in these automated checks, you know, also just look at other things like, oh, you've done a randomized trial, you haven't mentioned blinding, like, you know, really simple things like that. And together with some other colleagues as well, we're just looking at if people have got a sample size calculation. Now, can we recalculate the sample size calculation and check that? And if it's in error, or if we think there's an error, you know, send a little email to the researcher. All right, I'm almost done. So back to Doug Altman. So in 1994, Doug wrote a very influential paper in the British Medical Journal called The Scandal of Poor Medical Research. So almost 10 years later, Doug said he wished he'd said bad instead of poor, because he felt like he was being kind of too understated back then. Well, you know, we're another, 7 years down the track now. Doug isn't no longer with us, unfortunately, died before his time because he was still producing fantastic work. I think the adjectives need to get stronger because I'm seeing the same problems over and over again, and I'm not seeing the quality increase. So I would go stronger than even bad. And I mean, just to pick on one little study I read the other day, these people looked at randomized trials and found that 1,000 out of 1,659 of these randomized trials from the Cochrane database were at a high risk of bias. And they estimated the cost of bad trials was £726 million to £8 billion. And there's the link. And I should say all these slides are online, so you can find. And also what they found was if you were a participant in this whole suite of trials, you were more likely to be in a bad trial than a good trial. And, you know, and that's very disappointing for the public. That really undermines the public actually have very positive feelings about science. But if we continue to serve them so poorly, I think that confidence is going to be eroded. Okay, I'll stop there and I'll stop share so we can see people. And I see there's been some questions. I'm sorry for rambling. I went longer than I wanted to.
Well, first of all, thank you, Adrian. That was a brilliant presentation. Thank you very much. A few of us in person, but I can see there is a lot of people online. Just going through maybe some of the questions and comments from the chat. Does anyone else have an urgent question?
Okay, I can see. So scientific reports reputation has been questioned by university leadership because it publishes unimportant negative studies. Yeah, Alison, I think that's a very good point. And yeah, I've been having a bit of a debate with people on Twitter recently about that negative thing, and people kind of saying really weird things like, well, why would you publish a negative study anyway? That doesn't help your career. And yeah, I mean, and oh, why would you listen to PLOS One? Because they publish negative studies and things like that. I find that attitude so bizarre. And I think that's, for me, that's again, a real worrying marker of how far we've come, that a negative study is a reflection on you personally, like, oh, you must have done something wrong. Not that, you know, just this pill didn't work, or this new treatment we came up with didn't work. And yeah, that's really worrying. We definitely need to accept, and I'll call them failures. They're not really failures. If you've done the science right, it's not a failure. But yeah, we need to be far more mature about that and publish all this negative stuff and get over that.
Yeah,
sorry, Alison, you're going to say something.
Yeah, I was just going to say, I think we've got to really push it. If all of my experiments work in a lab, I get nervous.
Yes.
Because there's no way they're all going to work. It's just based on technical error, let alone whether my hypothesis is right. So, yeah, I think there's, you know, and I promote that sort of attitude in my group that, you know, if you get something wrong, let's figure out, you know, if the data is not interesting, let's figure out if we got something wrong, or it's just because the data is not, that's what the answer is. It's not. Yeah. So yeah, and I think, you know, leadership and I do have a role in this. It's really important to start communicating that. And, you know, we have so many measures of whether you're publishing always in Q1 journals and all that kind of stuff being so important. And, you know, it's just perpetuating and feeding into the problem.
Yep. Yeah. And my colleague Glenn Begley says, if you've got a paper in Nature, I'm suspicious of you. Because how did you get that paper in there? Because Nature publishes the most crazy breakthrough research, which sometimes it is a crazy breakthrough, and sometimes it's because you did something wrong in your lab.
Yeah, and you know, always, you know, 7+ years down the track, that's been brought back to what reality is by everybody else trying to repeat or do the data. And I find them the worst because their methods are useless. Yeah, any journal,
methods tucked away.
Their methods are all tucked away, and that's a problem that a lot of the top journals limit methodology space.
Yes, I know. Yeah, and I've been working with some people in this hospital data, and it was, you know, I did survival models, and the comments I get are, "Oh, Adrian, these methods are too complicated. We just don't understand them." And I'm like, okay, that's fine. I said, well, I tell you what, next time let's not do a complicated study then. Let's just do a little chi-squared table with a 2x2 and we'll stick there. But if unfortunately, if you've got a complicated question, it might need complicated methods. And I'm all for one for making things as simple as they are. But yeah, you can't dumb this stuff down just to make it understandable. I mean, I think I'm going back to that Lancet paper. I presume that's what they did. I'm guessing that's why they didn't use a survival model, because they didn't know what it was. It was too complicated for them.
Yeah, creating the tool, like you said, I think is really good and working with journals, because I mean, we've been able to shift the dial on things like Western bot data is known to be one of the most fraudulent pieces of experiment. Now all the journals have software built in that they can start looking for whether or not there's suspicious blots and stuff in a paper, and that's quite highly scrutinized through the review process. So if there's some automated ways that can raise red flags through journals, that would be helpful. Yeah.
So Wiley last year, the publisher Wiley, hired 8 people just to look at graphs. So that was actually a big investment. That, going back to that derailment, that is a derailment that has actually caused because that caused them so much embarrassment. But unfortunately, talking with the journals, and this has happened elsewhere, like in Holland, there was a big embarrassment and they set up a department to look at these issues. It almost needs the derailment. It needs a big embarrassment for anything to happen, which I think is worrying, because then we're still carrying on having these little mini accidents all the time. Why do we have to wait until something really bad happens to do anything about it? All right, sorry, I should go on to the next question. Thank you for that question, Alison. Too much unexplained variance. Lam, what did you mean by that?
I think, in my opinion, I'm going to ramble on a bit as well. Statistics is like the science of uncertainty, but humans hate uncertainty. Especially when you're talking about medicine, you want a yes, no. So that's why they use a p-value. And for example, even if you're going to use a probabilistic method, they probably still put a threshold on that so they can have people just above and below. I mean, thinking back to the days when you had a pregnancy test and you get your ultrasound and you get the probability of a Down syndrome baby of this. Everyone does the test because they want to, 0% probability of getting this result. But if you've got a low probability of having a bad outcome, I don't think the human brain can really deal with it. And I think that's causing a lot of these problems in statistics. When I mentioned the comment about too much unexplained variation when you're talking about prediction models, but clinicians want the prediction models because they want it to help decision making. But coming from a background in physics where you've got laws of physics, you can conduct experiments that control for pretty much every source of variation. There isn't a law of human behaviour or human biology as far as I know. So it's something that's going to be an ongoing tension, I think, between statisticians and clinicians.
Yeah. No, you're dead right. So one little technique I do that's very handy, and because with our Markdown, it's very handy. You can create, I can create an entire report for an analysis. And then what I will do is, before I show it to anybody, I will create a new treatment group that's totally random. And I will rerun all the analysis on that random treatment group. And then I'll send the report to everybody and say, here you go, here's all the tables, here's all the graphs we're going to use. Don't worry, don't interpret anything yet, because it's just noise, but you can see what the graphs and tables should look like, and do you agree these are all the right analysis? And then once we agree they're all the right analysis, I'm going to use the real treatment group, and then I'm not changing any analysis. What happens sometimes is you will get a significant p-value for the treatment. And some people will go, well, how did that happen? They don't understand that that can just happen at random. And that, I use that technique to try and prevent this multiple reanalysis of the data set, which I've had happen to me a lot. But it's also been an interesting technique in just teaching them a little bit about this uncertainty. Yeah, sometimes you can just get a p-value from noise that looks really small. From Aaron, how do you suggest that clinicians find and engage with statisticians to prevent these issues? Look, Aaron, I think that's a real problem because there aren't enough of us to go around. I regularly turn away work. I regularly get approached by people and say, look, I'm just way too busy, which is one of the reasons why I'm looking at robots. I have met clinicians that have been able to teach themselves statistics to a fairly high level. So I would encourage, in this gap that we have, I would encourage clinicians to do that. I find it funny, the clinicians will go away on these courses, and if somebody brings a new shiny machine in, they will go on the course and they will learn how to run the machine, but they will not spend time learning how to do statistics. Oh, because maths is hard, and oh, I was never good at statistics. Well, I wasn't naturally good at this either. I'm only good at it now because I've repeatedly practiced it over and over again, and I still make mistakes. But I have a one-day course in statistics, and it's not a one-day course in statistics really. It's just a one-day course in here's a whole load of stupid stuff that people do and don't do it. And I've had to cancel it about 3 or 4 times here in Brisbane because I just can't get enough people to come along. And people are like, oh, Adrian, yeah, I did want to come to your course, but it was a bit busy and had to get this paper into the journal. And then and they send me their paper and it's all the same mistakes. So I don't understand why clinicians and other allied health researchers don't see this as a good investment of their time, something that could set them up for the rest of their career, or at the least just stop you looking stupid. I thought people
that would
were
be the best selling point.
Sorry, Aaron, what was
that? That would be the best selling point. So you don't look stupid. I love that.
Except it might mean that they have already done stupid things and it'll uncover it.
Undoubtedly.
Sure. Yeah. And I've got some papers in my past that I definitely would be better now. I think we all do. I think I'm not here to, okay, I have laughed at some of those graphs and stuff. But generally I do try and be nice and I do try and be constructive. This is always about improving and getting better. What worries me is there doesn't seem to be any appetite for wanting to get better. There just seems to be an appetite for getting it in nature, for getting it in science, for getting it in the Lancet. Regardless, sometimes even being in meetings. I was in a meeting the other day with a bunch of clinicians. It was an hour long. We had a 45-minute discussion about what journal it was going to go to, a 15-minute discussion about the science. And I was just so depressed by that. And it was a group that I didn't feel strong enough to stand up and say, this is wrong. But I reckon that's going on everywhere. We've got the balance so totally wrong.
It's a very interesting point that you raised, because the reward for the clinician is, as you said before, the promotion, and partly that is governed by what papers you publish and where they get published. And it's the same in academia as well with grants and such. That therein lies the problem. It's not about the time investment and the quality of the work in some instances. It's about where you get it in and how it's received by the collective, who may or may not know statistical analysis at all. Yeah.
I mean, in clinical journals, I've regularly had fights with so-called statistical reviewers about things like the fact that, your data isn't normally distributed. And I'm like, what statistical training have you got? Where does it say? In what statistical textbook does it say all data has to be normally distributed? The world would be a very boring place if things were normally distributed. We'd all look the same, for one thing, or very similar. Variance is the spice of life, but some people have learned a little bit, and in some ways I feel, that there is explanations for this, that they've been trained that way, that some of these problems are now so ingrained. You can have like 3 generations of researcher, their researcher father and their researcher grandfather have been doing it wrong all this time. So of course they're not going to change.
No, that's too true. No, thank you for that.
Adrian, if I can just follow on to this, it's also for us as statisticians, how do we go in improving ourselves and moving away from these bad mistakes? Because to be honest, the way I was taught statistics many, many years ago now was probably, very much rely on those p-values, so on. And so I want to have different conversations, not necessarily the course that I encounter are providing me with a more enlightened statistics. Sorry, my voice is gone. So
yeah, I did a nice talk for a bunch of young German scientists the other day, and this question came up. They said, well, if I can't use p-values, what do I do? And I was like, well, and I didn't give a very good answer, but later on I wrote something and I sent it around that group. Sometimes interpretation is really hard. I actually think as well, we should celebrate that. Sometimes you get the results and they are a bit weird, or they are a bit marginal, or they are a bit positive on one, negative on the other. That's great. Science is hard. We should celebrate science being hard. But reviewers don't like that. Going back to what Lan said, they want this, a lot of people want this yes, no answer. So much stuff in research is not yes, no.
Mm.
It's kind of like, well, maybe, or, we think so. Or yes, if this is true, but not if that is true. That's a wonderful thing. That's why we're all still employed, because there are so few yes and no answers, because so much stuff is this horrible shade of grey that you can stare at for ages and say, well, is that dark grey or is that light grey? I don't know. What do you think? Talk to people, talk to your colleagues, show it to people.
That definitely is. I often find statistics is like you are bound to make a call, and that comes with like experience, how many things you've seen before, and it's good not to be isolated. I think that's why the Statistical Society is wonderful, because we can have these conversations. So yeah, thank you.
I'll go on again. You got your hand up.
Can I just say something too? Really following on what you said, Adrian. I think we as statisticians, first of all, I absolutely agree with Barbara that there is that there should be a better standard for reporting, acknowledging that one number cannot be the answer. We can't just use one number to say, let's use the p-value. Obviously, we need to look at what type of assumptions we made in our analysis, and looking at how the model has satisfied those analyses, and not just look at the p-value. I personally am not a p-value. I think p-values should be abandoned. There are so many good rationales for that and explanations on the American Society. I apologize, my daughter is playing drums next door. So the idea for me is really that sometimes it's a two-way problem. One is we try to make clinicians happy and give them what they can understand, but at the same time we also need to make a mea culpa, and because sometimes we are, in doing this, we are trying to make things simpler, not simple, like Einstein would say. We are trying to sometimes dumb down things just because, as you said, clinicians don't understand methods, or and in discussions with other colleagues also, there is sometimes also the lack of professional development, or as feedback on our own abilities. I mean, I have had conversations with other statisticians who said, oh yes, but I couldn't use the t-test because the data wasn't normal. And I can't understand why it is still so ingrained, this belief that what we are looking at is not the sampling distribution of the mean, but the distribution of the data. And like you showed, bimodal data, for some people would be totally unusable in their view for a t-test. Our data isn't normally distributed, so we can't run t-tests. So I was just trying to say, sometimes there's also, especially in Australia, or in Adelaide and smaller universities, or in smaller groups, there's less opportunity for professional development. Sometimes this type of misunderstandings cannot also get addressed. I don't know if I'd said something controversial here, but I think there is a proportion of statisticians who, because the statisticians, they don't get feedback from colleagues easily, because as you said, there aren't enough colleagues to go around. I don't know if I made my point across.
Yeah, no, I think you're right. Look, there's only 1,000 statisticians in the society across the country, and that, you know, a lot of them are not in health and medical research. That's split over all those different cities. So no, I don't think there are enough of us. And look, I think the Stat Society do a nice job. You know, the mentoring scheme is a good way of pairing people together. But still, yeah. And then some of these statisticians, yeah, will be the only statistician in the department. You can't go down the corridor and say, "Oh, I've done this. Does this look right? Is this a good idea?"
Absolutely,
yeah.
so important, isn't it?
It is really important, isn't it? Yeah. But what's happened is, unfortunately, we've got to this stage where we're so small and we're so busy.
Yes.
That we don't have the time to lobby for this stuff and lobby for more money. I don't know if you know, but like the Pharmacy Guild of Australia have become incredibly powerful. And I'm not bagging all pharmacists here. I'm just pointing out that they're a group that have managed to become, they got really organized, they're really powerful. They can now sort of afford to employ people. Just, you know, if the government brings up a policy that the Pharmacy Guild of Australia don't like, they have people that are onto it. You know, when the government makes stupid policies about statistics, or, you know, not taking statistician off the skilled migration list, you know, it's like one person at the society, the president, who might quickly write a letter in between doing about 10 other things. So yeah, it's a critical mass issue.
Yep.
Absolutely.
Sorry, Alison's had her hand up. Go on, Alison.
Yep, thank you.
And so as a non-statistician, can I ask a really potentially naive question in that you raised the point that we've kind of already cleaned away all the low-hanging fruit, and we're starting to get into looking at much smaller effect sizes. And so are those studies now even more susceptible to really bad statistics, because, you know, you've really got to pull out the nuance versus those lower hanging fruit that did have big effect sizes, and so you could really, you know, be pretty crap at it and still not get it wrong?
Yeah, look, I think so. Unless you want to go and work in developing countries, of course, because there's still huge health gains to be made there, huge things. But no, I think that's true. Well, I mean, of course, one thing is with smaller effect sizes, you need bigger sample sizes. Actually, the trend in clinical trials is going the other way. Yeah. Sample sizes are coming down. So yeah, I mean, straight away, there's one thing you can do. But yeah, if you've got more complicated questions with potentially more confounding, then again, yeah, you need.
And I remember seeing a seminar a couple of years ago, actually, from a health services researcher who was trying to make the argument that we're doing too big a trial designs and we're overpowering these things, and that NHMRC is spending too much money on these.
Oh, that might have been Nick.
Yes.
Yeah.
I wasn't going to mention names, but.
Yeah, no. I was part of that too. Look, that's a bit more of a nuanced argument. What Nick was talking about is, so in a standard clinical trial, you have we have one primary outcome. Yeah, that's the way it's normally done.
Yep.
One reason we have that model is to kind of police people into putting all their eggs in this one basket. And the example we had was of a quit smoking study. And in that quit smoking study, it was a lifestyle intervention by telephone or something, you know, hey, get up and exercise. So that particular trial had multiple benefits. People quit smoking, their cholesterol went down, their weight went down. I think their quality of life went up. So it was a real winner across multiple schemes, across multiple endpoints. If you only look at the primary outcome, to find that, you need a lot more patients. If you use cost effectiveness, which is a composite outcome, which includes all the benefits to their lives and also includes the cost of the treatment, you can actually find for a lot fewer patients that is a wise decision. So it's cost. I really like cost effectiveness because it actually totally moves away from p-values making the decision to, is this worth the money? Do the benefits of this outweigh the costs? That is a much, well, if you talk to a decision maker from the hospital about a p-value, their eyes glaze over, they don't know what it is. If you say to them, this one returns more qualities per dollar than this one, you know, it's a much better conversation.
Maybe that's going to be part of the lobbying pitch too, to try and strengthen the influence of the society.
We lobbied for that. We were called dangerous and, I can't remember what the other adjective was, but yeah, we were really pilloried for that idea, for trying to move away from p-values. And
the other uphill battle is human behavior, because I remember hearing about a study that was done, I think it was on knee arthroscopy, where they wrote 2 versions of the paper before they actually analysed the data, and all the authors signed a document to commit to those versions irrespective of how the results came out. And then after the results came out and showed it had no benefit, so many of them still tried to tweak the version of the paper.
Yeah. Look, my technique, where I show people a random treatment first, and sometimes, the next stage is, well, I'll show them the real results, but with labels on it. And somebody said to me once, a colleague I've worked with for years, you don't trust me, do you, Adrian? I said, no, don't trust you, don't trust myself, don't trust anybody. Like, we've got to get over that. And I've seen the same thing. I mean, so for example, and I've talked about this on this podcast, I've given people bad results. The National Environmental Protection Council didn't pay me because they didn't like the results. The Australian Commission for Quality and Safety in Healthcare threatened to take us to court because they didn't like the results. I did a consultancy with a drug company. I won't even name them because I'm a bit worried they might sue. The other 2 can go to hell. But yeah, again, they didn't like the results and they just suppressed one whole part of the work, and we were powerless to do that. With the other 2, we published the results because that stuff has to be out there. These things didn't work. But yeah, people take stuff personally, and that's why we need these techniques. And I like that one. You sign people up to, look, here are the results, you agreed, but often that doesn't happen. I've been friends with so many people up until the point the analysis come out. And then they're like, oh, you did something wrong, Adrian. It's like, no, sorry, this is you. I'm just presenting the numbers. Your treatment, your baby doesn't work. I know you've worked on this for 5 years, but I'm sorry, you need to rethink it.
Well, I really appreciate all the extra insight that you gave us through the Q&A, and thanks everyone for participating. Again, Adrian, you've been brilliant. I hope we can have you again, ready to explore some of these topics more in detail. Maybe have a session on what to do.
Yeah, that would be nice. Yeah. I don't know what to do. You have to get somebody else to present that one.
Well, we can think about it.
Thank you.
I'll give you some time to recover from this one.
Okay.
So thanks again, everyone. And I hope to see you for the next monthly meeting, which I don't remember the exact date, but of course you will find the details on the calendar. So thanks again. And